We're seeing an N-butane structure, 1, 2, 3, 4 carbons, and it is shown in its thermodynamically more favored all gauche structure. You can see that along any bond you notice, there are no eclipsing interaction between any substituent. Between either you look through the C2 C3 sigma bond, or the C1 C2 sigma bond, or the this way the C1 C2 sigma bond. There are no eclipsing interaction, and so this is the thermodynamically favored rotamer structure for this. And now in this structure, suppose instead of these two, to take this C2 and C3 for consideration, suppose instead of these two hydrogens, we have single electrons present on these carbons. Then what happens is, immediately they want to interact with each other and rotate towards each other and form a lateral overlap. Now, to form a lateral overlap, they can come close to each other. In order to do that, because these are single electrons, the repulsions between these bonding pairs increases, and this flattens out, and you have a structure which is shown here as a double bond. Now this double bond, there is a restriction of rotation along this bond. Because of this lateral overlap, you have a restricted rotation, and these two substituents are diagonally opposite to each other, and so this is called as the trans double bond. When you have a double bond, you have a geometrical isomer. How does that happen? That is, instead of this kind of a thermodynamically favored structure, you can have these electrons being present in a thermodynamically less favored structure where these two methyl groups are close to each other. In this case, these electrons again can overlap, leading to planarization of these two carbons, and the structure that results from that is a cis double bond. As you can see, these two methyl groups are on the same side of this double bond, and these two hydrogens are on the other side, unlike in the trans. Now, because of this greater steric crowding in these molecules, the cis structures, unless there are any other stabilizing interactions, these cis double bonds are less stable than the trans double bonds, or the cis double bond structures have greater energy compared to the trans double bonds. Now, we saw these are two restricted bonds because of lateral overlap between the 1, 2 C single electron, C single electron. On the other hand, what can happen is these single electrons can actually donate to two bonds and hence form a cyclic structure which can also restrict the rotation along this bond. That can also lead to Cis-Trans isomerism. What I have shown here are two structures where this happens, where a same atom, that is an oxygen atom, forms both the bonds with this carbon and this carbon. In that case, you form an epoxide structure where it's a 3-membered ring, in which case also this rotation along this bond is restricted. You can see that these two carbons are not in plane, unlike the double bond that you see here. But still there is restriction of rotation. Similarly, this is a trans epoxide. Similarly, you can have a cis epoxide, as you can see here. There is restriction of rotation, but these two CH3 groups are on the same side of the restricted single bond. So this is a cis epoxide, trans epoxide, and similarly, due to this kind of a steric crowding, Unless there are any other interactions to stabilize it, the cis restricted structures, epoxides, are higher energy and low stability compared to the trans epoxides. So these are couple of ways by which the rotation along a bond can be restricted by direct lateral overlap or cyclization to give structures with restricted rotation. Both cases it leads to geometrical isomerism, where you have either a trans structure or a cis structure. This is how you get the geometrical isomers.